Hello, everyone, and welcome back to your channel where we discuss probability. Last time we were uh, finding how or looking on how to find the confidence interval for mu if the distribution is normal, but the sample size is not large enough. And we had this example, and I showed you how to find T alpha over 2 in degrees of freedom. If you remember, we had 15 degrees of freedom. And if alpha is 10%, then alpha over 2 is 5%. However, today, I don't know why I didn't show you that you can do the same thing and let the calculator calculates or let the calculator calculate your confidence interval right away. You don't have to do it manually. Last time, if you remember, we went to second distribution, and then we went to the inverse t to find a value of t of 0.05 because alpha over 2 here. Wow, that was wrong. Alpha over 2 because alpha is 10%, but since we are doing it on two-sided, we divide by 2, and degrees of freedom would be 15. However, you could have gone to stat and tests. Oops, stat and tests and go down to a t interval. So when you go there, you can enter the data, meaning if you have the 16 data points, you can enter them here one by one. But we don't have that. We have a summary statistics. We have the sample size, we have X bar, and we have S. So we select stats, we go down, X bar is 25.3, SX is 13.6. Notice SX, not SX bar. If you say SX bar, meaning S over root N. But when it says S of X, meaning your random variable, every unit, you have to enter S. Okay? Then your sample size, again, not degrees of freedom. You enter 16, not 15. So here I enter 16. It asks you what is the confidence level, meaning a 90%. So you enter 0.9. You don't say 90%. And then go and calculate. And sure enough, you get 19, 34, and 31.26, which we already have. It's just I didn't do it for some reason last time, so I'm showing it to you today. Unfortunately, what we are going to cover, your calculator doesn't do it. You can use a software, even Excel can do it, or Minitab, R or RStudio, Python, or you use tables like we will be doing today. So, first of all, so we are going to say this is confidence interval for sigma square. The variance of a population. Notice the variance cannot be negative. So unlike the z and the t, our random variable would go from 0 to infinity, meaning it will have a much longer right tail than it has a short left tail, a short left tail. So we call that positively or right skewed. Positively skewed, meaning the skewness. In fact, the skewness is the third moment. If you think of the mean as the first moment about the origin, the variance is the second moment about the mean, not about the origin. If it's about the origin, you get the expected value of x squared. In fact, very similar to the moment of inertia. I mentioned that before, but it's really exactly the same concept of the moment of inertia for those of you who covered that, especially if the mass is or the area is 1, because the area under the probability distribution is 1. So you can ignore the mass or the area if it's 1, and that becomes exactly the same calculations you do for uh, the moment of inertia. Anyway, so let's go back. We call the statistic, or we are going to look at the new statistics, a statistic called the chi-square. A chi-square takes two parameters, alpha, same as z and t, and nu, which is the degrees of freedom, n minus 1. So like the t, very similar to the t, except that it's a square thing. And it equals n minus 1 times the sample variance, S square, over the population variance. Notice that S square, remember S square was the summation for all possible values of I of x sub I minus x bar square over n minus 1, the degrees of freedom. So if I multiply these, the numerator is basically the sum square of the difference of each value and the mean in the sample. So every value in the sample, if you subtract from it the mean and square that, sum them up, that's the numerator. And the distribution of that random variable over the variance of the population is called chi-square. The chi-square looks something, remember we said that also can be written in a, well, we'll discuss that when we go into statistics. Anyway, here is the chi-square distribution. Of course, its shape changes slightly as the number of degrees of freedom changes. So you can plot one for 3 degrees of freedom, and then another for 4, another for 5, and so on and so forth. So this is the distribution looks something like that. And of course, again, the mode moves as the degrees of freedom increase. So if we construct a two-sided confidence interval for sigma square, sometimes we only do a one side, meaning I want to make sure to get an upper limit of sigma square, because sigma square, the variance, is a bad thing, right? I want, if it's a production line or if there are items that I buy, I want them to be as similar to each other as possible. Meaning I want to decrease the variance as much as I can. So I have to put an upper, if it's low, I don't care. It's better, right? So usually we drew an upper limit confidence interval. We calculate that and put all of alpha here. However, for the sake of this class, we are going to show how to do it for chi-square alpha and degrees of freedom, which is n minus, I'm sorry, alpha over 2 and degrees of freedom. And here I will have chi-square of 1 minus alpha over 2 and degrees of freedom. Similar to the t, but except that in the t we had a t alpha over 2 and degrees of freedom here, and negative t alpha over 2 and degrees of freedom there. They were exactly equidistant from the axis or from the zero, right? But here, the area in between, of course, would be 1 minus alpha. So if I want to construct a 100 times 1 minus alpha percent confidence interval for sigma square, I have to say, I want to find the probability that my n minus 1 s square over sigma square being greater than chi-square of 1 minus alpha over 2 and degrees of freedom less than chi-square of lambda over 2 and degrees of freedom, which is the large one, to equal 1 minus alpha. And you said, but I want sigma square. I don't want all the rest. So the first thing you do is you take the probability and you take the inverse of that. You make it sigma square over n minus 1 times s square. And what happens to the inequality signs when you take a reciprocal? Yes, there are two cases where you invert them. If you multiply everything by negative number, or if you take the reciprocal. So for example, you say 3 is greater than 2. So if you take the reciprocal, you say 1 over 2 is greater than 1 over 3, right? So it's the same thing. So that is greater than this guy, which is 1 over chi square and alpha over 2 degrees of freedom, less than 1 over that guy, chi-square 1 minus lambda over 2 in degrees of freedom equals. Then I'm going to multiply everything by n minus 1 s squared. So that becomes n minus 1 s squared over chi-square alpha over 2 in degrees of freedom is less than sigma square is less than n minus 1 s squared over chi-square 1 minus alpha over 2 n degrees of freedom. That is my confidence interval for sigma square. So let's take an example. Suppose you were measuring, like you are selling stuff and you say, okay, my box contains, say, 100 grams of, some crackers. So you get a sample and weigh every item and calculate the variability in it. And you want this variability, of course, to be as small as possible. So let's say you take a sample of size 10 and you found X bar, you want it to be 100 and you got like, of course, it will never be exactly 100. So let's say 99.7. I don't care at all. Do you see X bar used here? Nope. But just for completeness, okay? And then the sample standard deviation, let's say it's 4.7 grams. Okay? I'm sorry, let's make that gram square. So it's the variance right away. And I want to construct a confidence interval. The problem is I don't know chi-square alpha over 2 and degrees of freedom. I think you can get it from the calculator. I never use a calculator for that. I usually use either R Studio or Python, as I said. Let's see, I should have checked that before, but if I go, there is a chi-square here, but I don't know if this is chi-square for the, that's a cumulative distribution. I want an inverse, and there is no inverse. This will give me, if I give it a chi-square value, it will tell me the area to its left. No, so I can't do that. And this is probably for the goodness of fit, which we will cover at the end. Anyway, I have a table here for chi-square. So let's say we want to construct 95% confidence interval for sigma square. Okay? So I'm going to say sigma square is greater than n minus 1 is 9. S square, we said it's 4.7 over something less than 9 times 4.7 over something. So we want the chi-square. We want here chi-square. Notice here we divide by alpha over 2. So I want chi-square of 0.025 and 9 degrees of freedom. And chi-square of 0.975 and 9 degrees of freedom there. So here is the 0.025. Okay, here is the 0.025. And you go down, it tells you nu is 9 here. So the intersection is 19,023. And on this side, you get 0.975, which would be the smaller value. And 9, it gives you 2.7. 2.7. So sigma square, and then you can use your calculator easily. 9 times 4.7 over 19.023, 2.22, and 9.4 times 4.7 over 2.7 is 1566. And you can see that's a wide range of variance because it's a square. Notice that you can also find a confidence interval for sigma, which is the population standard deviation, by taking the square root of those. So if I take the square root of 2.22, what do you think you get? Roughly 1.5. You know, 1.5 square is 2.25. So this is 1.49. And if you take the square root of 1567, you get 3.96. And that these numbers, of course, are closer to each other because that's a square root or the standard deviation. Notice, as I told you, sometimes we are only interested in an upper limit. So if I want to do 95% confidence, upper 95% confidence interval on sigma square, I want all of alpha to be here. So that would be chi-square alpha in degrees of freedom. So my sigma square would be greater than 0, so we don't write that, just less than a number. And this number would be 9 times 4.7, and then you divide on by alpha equaling 0.5, not 0.25. And that's basically, you go to 0.05 and 9, you get 16,919. No, you want 0.5, right? You want 0.5, 16, yeah, 16.919. 16.919, and that would be 9 times 4.7 over 16.919. So sigma square is less than 2.5, which means sigma is less than roughly 1.6, 1.59 or 58. And that's more accurate, not more accurate, but that's what we usually are interested in, to find an upper limit on a 95% or 99% on the upper limit of uh, our variance. Okay. Um, and I think that's it for today. This is for the sigma square and also to show you how to find the t or the confidence interval for the t using your calculator. Again, I'm not quite confident if I should have to do all of that on, say, something like RStudio. Since it's free, you can download it and you learn how to do stuff like that, because there are some topics that I want to cover that won't be done without a computer. Like we will have to use simulation. Like I mentioned to you, something called the bootstrap confidence interval. And that would happen if, suppose I want to find the confidence interval for a mean of a of values coming from a distribution. I don't know what that is. It may be a Weibull distribution. And I want to construct a confidence interval. And for some reason, I cannot apply the central limit theorem because getting this data is so valuable. I can't get more, say, than 10. So I cannot apply the central limit theorem. Yeah, of course you can, but, but the answer would be erroneous, right? So that's why I'm not saying you can't. Of course you can. You can do anything, but does it make sense? That's the important thing. So maybe we'll do that, but the problem is I don't want to waste time on showing you how to download the software, how to understand, or maybe I will have. I think I did a video for my students years ago, maybe 10 years ago. If I find it, maybe I will upload it for you, and then we go from there. Okay? Thanks for your time. Wish you all the best and hope to see you soon.